Next, we can talk a little bit about Newton's law of universal gravitation. You'll actually also have a video from Smart Physics about this, but they use the concept of centripetal acceleration, so I needed to introduce that to you before you could understand their video. I'll just give a very brief overview of it. So the idea of Newton's law of universal gravitation is that every particle attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, what does that mean? That means mathematically that the force between two particles, let's say they have mass capital M and lowercase m, is equal to their product, which is capital N times lowercase m, divided by 1 over r squared, where r is the distance between them, and g is some constant in proportionality that we don't yet know. G is actually the universal gravitational constant, and like I said, r is the distance between the centers of the two masses. And remember, these masses could be very big, like the Earth and the Moon, but they're going to act like all their mass is collected right at their center at a single point. And we've talked about how you can use that's the center of mass. G is equal to 6.67 times 10 to the minus 11, that's supposed to be 10 to the minus 11, Newton meter squared divided by kilogram squared. This is the force that's acting between any two bodies. I know it's hard to believe, but this is a very, very weak force. How do I know it's very weak? I know it's very weak because when I'm not attracted to you when I come near you. So two things that have very small masses are not attracted to each other very well. If I try to stick something to a refrigerator, I need to use a magnet. The magnet can hold the paper up on the refrigerator, but the paper itself does not attract to the refrigerator, even though there's gravitational force between the two of them. And that tells me that magnetic force is much, much stronger than the gravitational force between those two things. So although it seems like gravity is a very strong force to us here on Earth, it only seems that way because the mass of the Earth is so, so large. And so that makes the force that we feel actually something that we can measure. If the two things have very small mass, like your refrigerator and a piece of paper, then you actually don't feel the gravitational force between those things. So we've been using F equals ma, or the weight equals mg, where g is 9.8 meters per second squared on Earth, and that's an approximation to this force due to gravity. So that implies that as you move away from the center of the Earth, that the force that you'll feel from gravity will change. So when you're on the Earth, meaning that r is equal to the radius of the Earth, then this force must equal to the weight. But as you get further out, then r will get bigger, which means the force will get smaller, so your weight will get smaller. So let's ask the question, how does the force of gravity change as we move away from the surface of the Earth? So more specifically, how does the acceleration caused from the force of gravity change as we move farther away from the surface? We do have enough knowledge to solve this. We can start with F equals ma, and we know that force is the force of gravity, and so we can say ma, or ma sub g, which is the acceleration due to gravity, is equal to g m little m over r squared. We can cancel the little m's and solve for the a sub g, and we get g times capital M over r squared. That means that lowercase g, 9.8 meters per second squared, is just equal to this big G times the mass of the Earth divided by the radius of the Earth. We can actually plot the force due to gravity as a function of the separation distance between two bodies, and we can see that it follows this 1 over r squared term, as you would expect. So as you get farther away from the Earth, the force due to the Earth gets smaller and smaller on you.